Section P.3 is going to take what we did in P2, talking about exponents, and it's going to add another layer to it. Specifically, it's going to talk about rational exponents. We talked about rational numbers last class period. They were fractions, basically. Fractions are decimals that stopped. That's what we looked at. So we're going to look today at rational exponents in this section. And this actually harkens back to radicals. So I would like for you to remember something about radicals, and this might be something that you didn't see very frequently or often enough that you might not actually remember it, and that's okay. But this radical notation, that little n right there, is called the index of the number. When we don't have that there, you see on the bottom end, there's an understood 2, right, because it's a square root. That part you might remember, but the part that you might not is that this can be written as an exponent that's a fraction like this, which would mean this fraction is to the power 1/2. So everything that we did in the last section with exponents has a corresponding piece that applies to radicals, because radicals can be written in exponential form. There are two product rules that come about very nicely from this for radicals. One of them talks about what happens when I have a index where there's multiplication underneath, right? A times B. I can actually separate those into individual radicals if that's more helpful to be used in that way. And the reason I can do that is because I can actually rewrite this as AB to the 1 over n. And I have the ability from the properties in the last section to move that 1 over n through, right, as an exponent, and then I can turn it back into radical form. So that's the sort of reason that that works, and it does work very nicely. I have the same ability with fractions or numerators and denominators here. I can separate the radicals like that. So if underneath the radical you have multiplication or division, these properties exist. If underneath the radical you have addition or subtraction, no such property exists. It is absolutely not true that the square root of a plus b, it does not equal the square root of a plus the square root of b. You cannot do that. It's really important because it sort of feels like you should. I can just distribute the radical to everything. Well, you can't, and I'd like to show you a really easy example to see why. I'd like to use the example, we'll go with 9 plus 16. What is 9 plus 16? 25. What's the square root of 25? 5. Fabulous. If you were able to do what I just said you can't do, you'd be able to rewrite it like this. What's the square root of 9? What's the square root of 16? What is 3 plus 4? Yeah, oops. In particular, it is not 5, right? You absolutely cannot distribute radicals across addition or subtraction, but you can with multiplication and division. So let's take a look then at actually using that property with some examples here. So what we're really going to see is we're going to see rational exponents, and we're going to turn them back into radicals because it's easier to work with radicals. They're more familiar and comfortable to us, and we have these wonderful properties that we get sort of for free because of the rational component that we just dealt with already with those properties. So I can actually take this, and I can recognize that a power of 1/2 is the same thing as a what? Square root, you betcha. So this is a square root of 1/4. And the property over here, the second one with the quotient rule, says I can separate that radical to be on the top and on the bottom. And what's the square root of 1? 1. And what's the square root of 4? 2. So we get 1/2. Again, if you take your calculator, depending on what kind of calculator you have and the capabilities that it has, and you put this in just like this, it very well may jump you right to the end and tell you that the answer is 1/2. And if you want to use that to verify that you're doing it right, that's fabulous. Please don't use that as your only means of getting the answer because I expect to see some of the steps in between. That's how we would think about it. We would think about it with radicals. Number 2 specifically chose this one, again, because we've got that negative going on. And I want you to recognize that that negative has absolutely nothing to do with the exponent. So yes, there's a negative there, and we can write it down, and then we can rather ignore it for the moment. I can really talk about the fact that I have a 144 raised to the power 1/2. And just like on the last problem, a 1/2 is a square root. So this is how the problem changes. That negative is not underneath the radical. If it were, we'd be in section P.7. We'll get there eventually. But if it were, I wouldn't have a real number, okay? Because I'd have a negative underneath the radical, and that's not a real number. I do think you probably know, what's the square root of 144? 12, you bet. So this is negative 12. Because there's some examples with just some numerical values. So we're going to move in number 3 into stuff that has exponents, bases that are variables now. All right, so there's a couple different things that you could do. You could move the 3 through first, right? We could do that. Or you could combine the y that's on top with the y that's on bottom. Either one's acceptable. Which one would you like to do first? Distribute the 3 or combine the y's? Combine the y's. All right, so we will combine the y's. What that means is that I will have x to the 1/2. And then I have one of the ways to combine the y's is subtraction. This y has a power of 1, so I have 1 minus 1/2 on top. And then I have that same power 3 outside. So I have x to the 1/2. Maybe you already jumped to the next step I'm about to write down because you did the subtraction and you had no problem with that. That's great. What is what is 1 minus 1/2? Yeah, it's a half. So this is x to the 1/2, y to the 1/2. And then I have the power of 3. If you would like, you can change this into radicals now. I can write x to the 1/2 as square root of x. I can write y to the 1/2 as square root of y. And then I can deal with the power 3. It's fine to do it that way. Or I can distribute the 3 now. So I'm going to show you both of them so you can decide which one you kind of like better. They just kind of work in a different order, a lot like the things we were doing in the last section. I'm going to change them into exponent or into radical form right now and show you that way first. So the first option would be to change this into square root of x, square root of y. And then the fact that this is the power of 3 means that I have, well, it means right now that I've run out of room. Let's shift this over here. That I have square root of x, square root of x, square root of x. I have 3 of them, right? And then I have square root of y, square root of y, square root of y. So what happens when I multiply square root of x times square root of x? You get x, right? Square root of 2 times square root of 2 is 2. So yeah, this is x, square root of x. And then the same thing over here, 2 of these would be y, square root of y. Or if you prefer, you can write them as xy at the beginning, and then square root of xy either together or separate underneath radicals at the end. That is the final answer that we're looking for, by the way, is either of these versions, actually. Ugh. Either of these versions would be okay at this point. Because that's what happens if you change them into that radical form right away. Let me show you what happens if you distribute the 3 instead. So if you distribute the 3 instead, you're going to have 3 times 1/2. Well, what is 3 times 1/2? 3 halves. You can write it as 3 halves or you can write it as 1 1/2. I'm actually, oddly enough, going to write it as 1 1/2 for us for the moment, just because I think it shows more naturally what's going to happen next. But 3 halves would be fine. And I would have the same thing for y, yeah? 1 1/2. Well, what does 1 1/2 mean? Well, it means you have one of them, and then you have a half of them, right? I have one pizza, and I have another half of a pizza. Well, one whole pizza is just x. And then that half part means I have the square root of x. One whole y means I have y, and then the square root, or the half y, means I have a square root of y. And I get to it this way. So a mixed numbers approach is actually very friendly if I do it on this particular problem. any questions on that one? Because that's a little bit funny. We haven't dealt with anything like that yet. Is that all right? Okay, let's try another one then. So as we shift to this slide, you'll notice that we're shifting and we're not dealing with a square root anymore. This one is actually a cube root, right? Okay, it's already written in cube root form. It could start out written as to the power 1/3. It just didn't. But cube roots have that same property that we had over here for radicals when we did them with an index of n in general. So just like I can sort of, it feels like distribute the radicals through multiplication, and through division, I can do it even when the radicals are not a square root. I can do it with a cube root. So it means I can actually have the cube root of negative 125 on top and the cube root of 8 on bottom. Cube roots aren't quite as familiar with the way that we think about them as square roots are, but these numbers aren't terrible. You can find a lot of your perfect cubes pretty quickly just by going through what is 1 time, what is 1 cubed, it's 1. What is 2 cubed, it's 8. What is 3 cubed, it's 27. What is 4 cubed, 64. And what is 5 cubed, 125. And I'll stop right there because I've encountered both the two that are a part of this particular problem. They're not very big radicals. If I had numbers like 12,500, I need to factor some things out to actually make that work. But 125 and 8 are fairly small numbers for the purposes of cubing and cube rooting things. So the cube root of 125 is actually 5. Now, it's very interesting that this one has a negative underneath the radical. I mentioned earlier in the problem when we had the 144 that it was sort of providential that the negative didn't apply to the radical because if I put a negative underneath the radical, I'd be in section P7. That's what I said. And that's a true statement. The difference is that that was a square root and this is a cube root. And if I multiply 3 things together, I can still get a negative. It just meant that they were 3 negatives that I multiplied together. A negative times a negative times a negative is still negative. So this isn't just it isn't just 5, it's actually negative 5, because negative 5 times negative 5 times negative 5 is negative 125. It works when I have indexes that are odd. I can do that. On the bottom, what would the cube root of 8 be? 2. And again, that's because 2 times 2 times 2, or 2 cubed, is actually equal to 8. So we end up with this particular fraction, and there's no reason to change that into a mixed number, like none under the entire sun. It's perfectly fine to leave it as negative 5 over 2. If we could reduce the 5 and the 2, we would, but we can't on that one. 5 and 2 don't have any factors in common, so we're done. Number 5 is a little bit odd looking because I have a 3 over 4, and we haven't seen that happen yet. We've only had something that looks like a 1/2, or we've talked about a 1 over n, or in the case of the last problem, a 1 over 3. But this one actually says 3 over 4. So what does it actually mean happens? Well, what it actually means happens is, first of all, there's a negative on the outside. It's not affected because there's no parentheses, right? It's just on the outside of the radical. This little 4 means I have a 4th root. And the 3 is just on the 2. It's just 2 cubed. So that's how we would rewrite that. In general, if you want to sort of jot this down, in general, if you have the mth, actually let me write it this way, a to the m over n, it will be the nth root of a to the m. That's how it always works. The numerator is still an exponent, the denominator becomes the index. Okay, so what do I do next? Well, I do 2 cubed. What is 2 cubed? Y'all know it. It's 8, yeah. Now, there's no way to simplify that and take the 4th root of it. The reason I know is because 2 itself can't be broken down, right? Over here, 2's prime. I can't break the number 2 down any smaller so that it has some component that's raised to a power 4. That's not possible within the integers. So at that point, I'm actually done. It feels funny to leave it written that way, but there is no other way that you could leave it written. You're done. I don't have a lot in the way of directions written on here, but what I wanted us to be able to do in these problems is to be able to move in and out of that rational exponent and the radical notations. So if you were to see directions written on number 5, it would say something like simplify in radical form. And if you were to see directions written for number 6, which is starting out in radical form, it's going to say simplify into rational form, right? Turn it into rational exponents. So on this one, we're actually going back in the other way. We're wanting it to look more like problem number 5 and how problem number 5 started. So there's a 4 on the outside. The x has a power of 2. And then the index of the radical is a 3. So this has a denominator in the rational exponent of 3. So it's just written as x to the 2/3. They're not asking us to change anything. They're just changing the form. Okay, moving in and out of that form, simplifying when we can. There's nothing to simplify on that one. So it's finished. Is that one all right? Okay. 7, again, is written now in that radical form, and our goal is to simplify if we can. But 24, if you'll notice, is not a perfect cube. Right? I bypassed it. They go from 8 to 27, 24 somewhere in between. There's something else that I need to do on this particular problem. The first thing I'd like for you to recognize is that since it is negative and it is underneath a cube root, that just means I'm going to have a negative on the outside. Because if I multiply 3 things together that are negative, I get a negative. So the negative sort of feels like it's just coming out of the radical. Okay, it's not, but that's how it feels. This is an example of one where I really do need to break the 24 down and see what it breaks down into. So somebody give me 2 numbers that multiply to 24. Any 2 you'd like. 8 and 3. All right. You can do this one of 2 ways. Because of this being an 8, it's very nice. We can take the cube root of 8. It's 2. So if you recognize that at some point, you can use that fact and you can actually make it a 2 on the outside. If you didn't recognize that, or if instead of picking 8 and 3, you'd chosen 6 and 4, neither of which are perfect cubes, you would keep factoring. So you would factor the 8 down and you would maybe say to yourself, okay, well that's 2 and 4, right? And then, I'm sorry, I'm out of space, but you break it down again and you get 2 and 2. So I'm kind of all over the board, but I'll circle them. These are the 4 factors that I actually have. There's 3 2s and a 3. So I want to show you this in this way because this is more general than what the last one would be if I just pulled out the 8 and recognized that it's 2. But if you see that, you can do it. It's not a problem. So I've still got a cube, and I've got 2 times 2 times 2 times 3. And then there's actually 5 A's, so I'm just going to write them all out for a moment as well so I can show you how to think about this with all of them there. If it's a square root, we look for 2 identical pieces underneath the radical to be able to pull out, right? So like if the number underneath the radical were a 25, I can break it down into 5 and 5. The reason the 5's on the outside is because there's 2 5's underneath the radical. Because this is a cube root, I'm looking for groupings of 3. Anytime I see 3 items underneath the radical, I can pull it outside of the radical. These 3 2's would be an example. They would come out. So would these 3 or any of the 3 A's will come out. So I still have that negative on the outside. I now have a 2 and an A on the outside. But there are still pieces underneath the radical, which is a cube root, that I have to write in. I have a 3 and I have 2 A's, so I have A squared. And there aren't any more pieces that I can actually bring out on that one. Does that make sense? Is that all right? It's a little different because it's a cube root. Okay, 8 doesn't have any variables in it, but none of those radicals match, right? There's an 18, a 50, a 12, and a 75, and none of the 4 match anything else. So on that one, what we have to do is we have to reduce them much like we did the 24, but we have to do it now for all 4 of them. We have to factor them. So on 18, how will 18 factor? Give me an option. 2 and 9. 9 is 3 and 3. So we could write this as the square root of 2 times 3 times 3. How about 50? How will 50 factor? How about 5 and 10? We can do it as 2 and 25 if you wish, but 5 and 10 will work. 10 is 2 and 5. So I have minus square root of 5 times 2 times 5. Factor 12 for me. Tell me something. 2 and 6. And then 6 would be 2 and 3. So I have an addition sign, and I have 2 times 3, in whatever order you wish. How about 75? 25 and 3. And then 25 is 5 and 5. So I have minus square root of 5 times 3. So whether you actually show me this piece right here, I don't necessarily care, but you have to show me either this one, the one where it's got the factor trees that I've sort of drawn, or you have to show them to me underneath the radicals. That's the work. That's the factoring piece you're doing. So if you're showing me either of those, which you're looking for, because these are all square roots, right? And since they're all square roots, you're looking for pairs of things. The last one was a cube root, so you're looking for groupings of 3. These are square roots, so you're looking for pairs. So if you're doing it from the factor tree, you notice that there's a pair of 3s. You notice there's a pair of 5s. You notice there's a pair of 2s. And over here, there's a pair of 5s. You're looking for pairs. If you're looking for it here, you've got the same thing. You've got a pair of 3s. You've got a pair of 5s. A pair of 2s, a pair of 5s. So what does that mean? Well, it means when I rewrite this, I have the 3 on the outside, and I have a 2 still underneath the radical because it didn't pair up. Right here, I have a 5 on the outside and a 2 underneath because it didn't pair up. And you can see, for example, on this one, I can see that from here, that it didn't pair up underneath the radical, or I can see that up here, it didn't pair up underneath the tree. I don't care which one you use. It depends on your sort of visual perspective. But one of those two allows you to see that the 2 should still be underneath the radical. Over here, the 2 is on the outside because it pairs up and the 3 is underneath. And over here, the 5 is on the outside and the 3 is underneath. That simplifies all 4 of the radicals, but now some of the radicals actually match. So what do I mean by they match? Well, I mean the piece that's underneath the radical match. It's called the radicand. So the piece that's underneath here is a square root of 2, and here's a square root of 2. Those two match. What that means is that these two are like terms. I have 3 radicals of 2, and I have 5 radicals of 2, and they're subtracted. And 3 minus 5 is negative 2, so I have negative 2 radical 2. And then these two actually happen to match as well. They wouldn't have to, they just do on this particular problem. So I have 2 of these minus 5 of these, which gives me negative 3 radicals of 3. And that would be my reduced answer. Okay, we're almost done. We'll finish up right on time, I think. So any questions on that one, though, before I flip the screen? Okay. Number 9 actually shows what happens when we have an exponent on these. So again, this is the properties of exponents back from section P.2. I can distribute the exponent because it's multiplication. So I can distribute it like this. Because it's a 2, if you wanted to, you could also just write it multiplied by itself, right? You could write down 3 square root, let me use white, 3 square root 5 times 3 square root 5, and you could reposition what things are next to each other. You have some options here. So either distributing or rewriting it times itself. You multiply the pieces that are outside the radical together. What's 3 times 3? 9. And what is the square root of 5 times the square root of 5? It's 5. Okay, when you multiply a square root by itself, a square root by itself, it eliminates the radical. So I end up with the value 45. If you think about it from this sort of distribution perspective, right, 3 squared is 9, and then the square root of 5 squared is 5, you still end up with the same 45. All right. Number 10, what I wanted you to recognize is that we don't typically like to leave radicals in the denominator. I'm not really sure why that's a thing, to be perfectly honest with you, but it's a convention of mathematics that has been around for quite some time. And so there's a way of eliminating radicals from the denominator, and I want to show you what that looks like on number 10. We'll be using it later on in some different areas. But what it actually means that I would do for problem number 10 is that I would multiply the denominator by itself. And the reason that I would do that is exactly what happened on number 9 with the square root of 5. Square root of 5 times square root of 5 is 5, right? So square root of b times square root of b is b, and I don't have any radical in the denominator. Like, that's the reason that that's what we're doing. The compensation that we have to make is that anything we do to the denominator of a fraction, just like we talked about last time before, and we have to do it to the numerator of the fraction as well, right? Whatever happens, happens in both locations. So I do still have a square root of b, I just don't have it in the denominator. So my numerator now is a square root of b. I think it would be difficult for you to convince me that that's better looking or simpler than it started with. It's not really the point. The point is simply that the radical is not located in the denominator anymore. And that was our goal, that particular problem. Number 11 looks really funny because I've got like a radical inside of a radical. But it's actually a lot like what happens when I have an exponent raised to an exponent. Right? What do I do when I have an exponent raised to an exponent? Well, I just multiply the exponents, right? Yeah? Well, I can actually do the same thing here. I have a radical inside of a radical, and I can just multiply the indices of the radical. So I can actually just multiply the 4 and the 3 together, because they're really representing 1/4 and 1/3 as exponents, right? So what is 4 times 3? It's 12. So this is just an extension of that idea of exponents being multiplied. I can multiply the indices the same way. All right, any questions on either of those last two? We're a little bit different. Okay, I'm going to check before y'all leave, so hold tight when you start moving things around and putting things up, just to make sure that everybody's submissions actually went through like we were hoping that they would. That way we can make sure if you are having trouble that we get that fixed right away. Other than that, sections P2 and P3 are now assigned, and they will be due on, we're on Thursday, right? So on Tuesday in class. So you have 2 different days. I'm pretty sure the Success Center probably starts on Sunday night. That's usually what happens, is they start the first Sunday night after we've been back in school a week. So if you do need to have questions answered, you should have Sunday night and Monday night both to talk to the Success Center. You have lots of options for setting up an appointment with me if you need my help specifically. All right, let me refresh this and we'll see if there have any ones that are not done yet.